Okay. So let me give you a little tip about what you can do to help you figure it out is go around to each carbon and decide how many hydrogen are on it. So that you can, or you can literally just write what its electron domain is, right? So you could do this, or you could just say, sp3, 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 right? You could do either of these, sp2, et cetera, right? Or you could go around and do this. You can write the hydrogen, right? I always just did this because I knew that I meant hydrogen by it, right? And then this, right? So then I was able to identify, okay, well, I can, you can see that this is, right, this is an sp3 here, right? So I know that my electrons aren't going to be able to be kicked that way. So that's a tip when you're doing curved arrow pushing, especially with resonance. Hey, Sarah, can we please go over question 10? Yep. Yes. We did question 10 in my last office hours as well. Question 10A, I believe, Miriam, I don't know if you got a chance to look at that. So anyway, so this is a great way to double check with your resonance on that one. Okay.
Okay.
Do we want to try this one?
Sure.
Okay. So it's asking, identify Lewis acid, Lewis base, or Bronson acid, Bronson base, and to do curved arrows, and to be careful to put them in the appropriate way to draw the transition. Does it say and draw the transition state and identify any partial bonds? All right. To go from here to here. So what do you think your first line of attack would be?
Identify the Lewis acid and the Lewis base.
And how would you do that?
Chlorine would be the base because it has the non-bonding electrons as well as the negative.
Nice. There you go. Off to a great start. Okay. Now what? How would you, here's the bond that we're looking to make right here. So how would you make that bond happen?
I think this is where I'm getting lost.
Okay. Let me ask you this. What part are you feeling lost about? The direction of the arrow, where the arrow should go, how,
I think both, like where the arrow should go and the direction as well.
Okay, perfect. Good. Yes, thank you, Miriam. She said add the arrow from the base to the acid. So you always want to add your arrow from the electrons to where they're going, right? So in this case, we've identified that the electrons, that is one of these pairs, right? But we'll just say that we're going to take these electrons and bond them somewhere on this Lewis acid. Where do you think the best place to bond onto this Lewis acid would be?
Probably on that sp3 carbon.
There's a lot of sp3 carbons. There's an sp3 here. Those are all sp3.
The last one.
This one?
Yeah.
Why do you choose this one? So let me draw this out. Where could chlorine go on this carbon?
Nowhere, actually.
Yeah, right? This is why sometimes it's really a good idea to draw some of these out so that you can see, right, how this all works. Now, I'm going to give you another big hint here. If you see a formal charge, go for it, right?
Okay.
So that formal charge is specifically on this carbon, okay? If you see a formal charge, especially if you see a formal charge here and a formal charge here, like, go for it, right? So that's where you're going to go. So you're going to start your arrow at the electrons and draw it towards where you're attacking, so they say.
Okay.
Right? And, you know, to be specific, you don't want to necessarily, you know, you don't want to be kind of ambiguous and say, here, I'm going to erase some of these hydrogens because now you understand what I meant by that. But let me just kind of clean this up a little bit so we can see better, right? You know, you don't want to like arbitrarily draw your arrow and just say this, or, you know, maybe draw your arrow and point it here, right? Because that's not, this is a bond, right? This is a bond
Mhm.
here, so that we're specifically attacking the carbon here. And so they will be particular about your arrows. So that's why I'm trying to emphasize it. Okay, yeah. And for this question, that's pretty much it, I believe, right? Because yeah, once we have to do the partial bond, the transition state. So if we were to draw the transition state, we have cyclohexane and our methyl. And then let's just draw chlorine over here. Okay. And then your, right, transition state. It's not a very good color to use, but whatever. This is your transition state, right? Just these like little, I should draw that a little bit better, right? Because now I'm not being obvious with my drawing. Right. So just draw your little lines to the electrons. This is supposed to be an electron, right? And then you just do like these little dashes from the electron to where it's going.
Okay.
Yeah. So, and this is your partial bond. So then, boop. And this just means transition state. Same thing when we do our energy diagrams, right? And we have like these, whoops, you guys get what I mean? Those are your transition states. That's what this means. This is like all this high energy that's going into creating this bond so that hopefully your electrons are in a lower energy state later on.
Okay.
This would be rounded, obviously, but you know. Does that help a little bit with some of the curved arrow? We can do another example if you want. And yes, Miriam, we will. Okay, I will check that now. What are we working on now? Are these are from, this is just from the homework site in the curved arrows section. I'll do one more of that, and then let me know if you still need help with number 10. We can always do number 10. I can do B. I did A yesterday, so these are more, so is it more resonance that you're like resonant contributors that you want to see curved arrow pushing on? Like, okay, so this is two examples. This would be more resonance and this would be more reactions, right? So what is it that you feel like your resonance, there we go. What is it that you're feeling?
Probably reactions.
Reactions? Okay, cool. Let me put another reaction in here. And that'll hopefully give Miriam some time to look at that. And then Jackie, I know you're always loaded with questions, so let me know. Hopefully you did your.
Before we move on from the CL one,
Yeah.
you did, there's two transition.
No, there isn't. No, I was just, no, ignore that. I was just trying to show you an energy diagram in general, just to denote what this meant. Just to kind of connect the dots for you. But no, it would be like this, right? I was just
yeah. Okay,
getting overzealous. Yeah. I was just like doing more and trying to just denote things for you, but no, ignore that part of it. So yes, that would be this.
Another question, because in the lecture she did say, if I think this is what she said, if I'm remembering correctly. She said if it's a Lewis acid and a Lewis base, it's also a Bronsted acid and a Bronsted base.
All Bronsted acid and Bronsted base are Lewis acid, Lewis base, but not all Lewis acid, Lewis base are Bronsted acid, Bronsted base. So remember, Bronsted specifically has to do with hydrogen, giving or accepting a hydrogen. But, and the next example we're about to do, you will see that it is. But Lewis acid, Lewis base only specifically has to do with electrons.
Okay, because like right now the CL only has electrons, and it doesn't even have a proton, so it wouldn't even be a proton donor, so it wouldn't be a Bronsted base, right?
Exactly. On this one right here, that's exactly right. All we're doing is the electron donating accepting rather than proton donating accepting. And you'll see this next one that I put up. Oh, good, it's already loaded.
Okay, perfect.
Yeah, so this one does specifically have a hydrogen in that, so we'll see that. Okay, so tell me. Okay, so we want to know what's our Lewis acid, what's our Lewis base, and we just already discussed what do they call it? When you give something away when you're reading a book. Anyway, this will also be a Bronsted acid, Bronsted base. Spoiler alert. Spoiler alert. No, foreshadowing, but yeah, no, spoiler alert. That's so funny. But yeah, so this will also be Bronsted. So however you guys, do you guys prefer to figure out to label Bronsted acids and acids and bases first, or do you prefer to do curved arrow first?
I'm good with whatever, like, you think.
Labeling.
Okay, labeling. All right, well, label away, my friends. Where are things? So what we're going to label is we're going to label our reactants. So we have reactant A and reactant B. Okay. So what is A?
A base. Oh wait, no. It's gonna be the acid because there's a double bond, so that must be the base, right? On B has a double bond, so I'm thinking if there's a double bond, you can break that and give electrons away.
Okay, that's a way to think about it. Yes. I'm definitely not saying that's wrong. I didn't think about it like that, right? When I see specifically something like this is an acid, right? HCl, HI, HBr, all those are all like your strong acids, right? So that's just something, and you'll see this, time and time again. So besides the fact that once you get to know these, you'll know immediately that, oh, that's definitely an acid because that's how it is. But also you have a hydrogen. The hydrogen is going to be a part of the bond breaking and making. So because remember, Bronsted acid specifically and Bronsted base specifically has to do with, I don't know why that just did that. Specifically has to do with donating and receiving a hydrogen, right? So let's just think about it straight from definitions. So yes, this has electrons that you could donate. So which would be Lewis acid or Lewis base, right? But also this is kind of because say this had another one, or say this had, and then you had Br here, right? But this has a double bond. How would you determine, so that's why I just want you to be careful a little bit about using a double bond as an identifying characteristic, because the molecules are going to get a little bit more complex and you're going to see double, triple bonds in things that, you know what I mean? Like might actually be your acid. So
that one must be the acid because Bronsted acids are the ones to donate. Yeah, Bronsted acids are the ones to donate the proton, right?
Yeah, exactly. Yeah, exactly. And here's the other good news. If it's a Bronsted acid, it's also going to be a Lewis acid, right? Like you're not going to have a Bronsted acid and a Lewis base. You know what I mean? So if you could figure out one, you've automatically got the other, right? Does that make sense? So as long as you can figure out which one's the acid and which one is the base, if you identify that there's a hydrogen in it, it's also Bronsted as well. Does that make sense?
Yes.
Perfect. And Avery, how are you feeling about this?
Feeling good.
Okay, so far so good. So we've identified Lewis acid, Lewis base. So now, where are we gonna put the arrows? Okay. And I will say that Miriam had a good point, right? In this case, we have this double bond here, and that's really the only one. If this is our acid, we know that these electrons aren't going to be doing the donating because we've identified that these are our acids, which means that it needs to accept electrons. So where does, you know, what electrons is this molecule going to accept? If this is a Bronsted acid, it means it has to donate a proton.
Mm-hmm.
So if this gets donated somewhere, let's just put an arrow saying it's going to go away. What electrons is this molecule going to accept? I'm trying to be explicitly clear that this is the piece that's going away. I'm going to give you a little bit of a hint.
It'll just go towards the positive sign, right?
There's no positive sign.
To the
What I'm
right,
trying
on the right, you know how there's like a positive right next to.
over here. Sorry, yes. Well, what I'm trying to say is like, what electrons is this molecule going to accept? So this molecule, if this hydrogen has to leave, this molecule has to accept a pair of electrons as well. And those electrons are going to come from this bond here, right? That's the only place that the electrons can come from. So we'd have our curved arrow pushing there. Does that make sense?
Sort of.
Okay, that's okay. All right, so I'm moving backwards a little bit so you can kind of see some of the process here. So now if this needs to leave, how is this hydrogen going to leave?
Oh, by breaking that bond in between and then dumping the electrons on the BR.
Yeah, exactly. Now this hydrogen isn't specifically going to do that. What's going to happen is another set of electrons are going to steal the hydrogen. And because the hydrogen can only have one bond, it's going to, and it's a very weak atom as far as like, it doesn't really care where it is. It's going to leave the electrons behind, right? So that's why we have this curve, that's why we have this curved arrow here. So now we have to figure out how are we getting this set of electrons to steal this hydrogen? So there's two options. You can either have the hydrogen connect here or you can have the hydrogen connect here. Well, the good news is, right, we already see our product. So we don't have to like decide on that at this point in the game. You will later on when we deal with Markovnikov and anti-Markovnikov, which you guys I think have seen now at this point. But so we know that it's going to have to go to this carbon here, right? Which means that, remember, and this is where those, the arrows are important. So when you're drawing an arrow, you're going to go from the electrons, which are here, right? And you've got to kind of come around this way. And this is in order to denote that the bond, imagine that this is like, have you ever seen like blueprints when they have like a door and they kind of denote a door like this, right? Do you guys know what I'm talking about? Like where the door they're trying to denote like the way that the door swings open, like in blueprints for like building houses or something. Have you guys ever seen that? No? Okay. Well, I was trying to make an analogy that you might understand. But okay. So just imagine that you need to decide, if we're deciding that this is the carbon that it needs to be attached to, right? We've already decided that here, that this is the carbon. So in this way, right? I'm going to erase this so we can see this so it's a little bit more clear. In this way, this carbon is the one that needs to be attached. So we could imagine that there's this dotted line here, right? And this will be a part of your transition state, right? So, but this is, so, but in order to do that, these have to go this way. They have to go towards, so you want to draw your arrow towards where your bond's about to be. Does that make sense? Versus if we drew the arrow, I'm going to do it in red. If we drew the arrow from the same thing in the middle of this bond, right? But we drew it this way, that means it's pointing towards the right bond. Do you guys see the difference here?
Yes.
Okay. Avery, how are you feeling?
Yeah. Yeah.
Okay. Cool. All right. So let's see if I can get rid of this red. Okay, perfect. And then, yeah. So that's our curved arrow. So we've got from the bond to the hydrogen, right? And remember, it kind of like swoops around. We don't necessarily draw it like, we don't point to the hydrogen. We kind of do this like swooping situation, right? Where we're like kind of parking up beside it, like a parallel park type situation, right? So we swoop in and we steal the hydrogen. And then because hydrogen can only have one bond, these electrons kick off, and bromine's happy to be a negative, an anion. And then, so because we've done that, now we've got our hydrogen here. But now we have, as you see, a cation here, a positive charge here, because there was some electrons that were here and that are no longer here. This, remember, is an sp2 hybridized carbon. And there's no more electrons there. So we can't just like assume that this hydrogen is here and then like get rid of this, right? Like that doesn't work like that. So we have to put that positive charge since we took some electrons from that carbon. Okay, does that make sense? So now, then we just draw our, whoops. Then we just draw our transition state, right? And so our transition state, here's that's our skeleton, right? And here's our skeleton, right? Because you need to do like whatever is consistent both in the beginning and the end, that's your skeleton, right? And then we identify with dotted lines the bonds that are being broken and made, right? So this bond is being broken, this pi bond. This bond is being made, and this bond is being broken, right? And then we put brackets in our transition state. And because our product, right, +1 - 1 = 0, we don't have to put any charge on this transition state, right? We have 0 here and 0 here. So there's no, +1 or -2 or whatever, right? That doesn't exist here. Does that make sense? Yeah, go ahead.
So in my mind, I'm like, okay, like there is like a positive or like a positive charge on the product, and there's a negative charge on the BR. Why didn't we put the BR on the positive charge? I don't know if that makes sense. Like my mind just wants to do that.
Yeah, of course. Well, so that reaction wouldn't it wouldn't necessarily happen like that. So this reaction in itself, because these are higher energy, this reaction is mostly going to be in this direction, So like we have like, we've talked about like kind of directionality where you have this like larger, right? Like you're going to have, this reaction's mostly going to go to the left, but you'll have these like transition states in these molecules that'll break off. But yeah, I think you started to get there, right? With like your reactions at the end, right? Haven't you guys? Oh, here's number 10. But you guys have started to see this stuff, right? You guys have hopefully gotten to this point since your exams today. This is the last bit of the material, right? So we start to see, so you'll see as you go along these other reactions with bromine. And as you go farther along, you'll see more of them. But a lot of it has to do with like how you have these catalysts here, right? These catalysts are needed in order to like make certain bonds happen, certain reactions happen. So as far as this reaction exactly as it is, it will mostly be to the, where did I put it? Oh, right here. It will mostly be to the left because we have formal charges on the right. We have formal charges in the products and no formal charges in the reactants. Does that make sense?
So we're basically trying to leave one with higher energy than the other so that we know which one's faster and slower.
This would be a way in which you could apply that concept. Yes. This question isn't specifically asking for that, right? But if you were, if it was asking, you know, which direction, where does the equilibrium lie in this reaction? The equilibrium would obviously, you know, lie on this side, right? The equilibrium lies on this side because of these formal charges here. Things like to be in the like least energy possible, right? It wants to, like, the universe wants to maximize entropy and minimize high energy. So, but yeah. How are we feeling about curved arrows right now? Avery, you feeling slightly more confident? How are you feeling? And there'll be more, you know, as we go. But Miriam, number 10, did you want to, what is there something specific about number 10?
So like
Yeah, go ahead.
number 10, part, wait, let me see.
Yeah, I have both A and B. I already did A, but I can like walk through it with you and we could do B together, you know?
So part B, she adds H3O. Like she goes, okay, so the H2O plus, you know, another H, and it's H3O. Like, where did that even come from?
You mean right from the beginning?
Yeah, like,
Yeah, she does this.
let me go to it, right? So
She does this.
yeah, and then
Mhm.
it's all of a sudden there's a new H, she adds an H, and then it's H3O, and that becomes the new base or the
Mhm.
new acid.
Yeah, because you have to start with the H3O, right? That's how she starts it, right? With H3O, not H2O, correct?
That's what I'm like, I don't think I remember doing that. Like,
Yeah, so and I just want to it's this right here. Right? Excuse me. So you're gonna start it off. So with this one, it's a you're gonna create a cation. So it's a good idea. I'm on here because I wanna highlight some things here, right? Rearrangements are possible, cation intermediate. Rearrangements are possible, cation intermediate, right? So these are things that are good to know because as you can see, the bond that we might necessarily be like is going to be this, but we end up with, you know, a hydrogen over here and then the OH over here, right? Instead of, you know, where you might expect it over here, but that's because we have that cation intermediate. So, and in this class, if the cation, if we can have a methyl or a hydride shift that creates a more stable cation, you will. Okay, so just that's like a common rule here. So my question is, did she start this with an H3O or with the H2O?
she started it with the H3O. So she goes,
Yeah.
okay, like this is our acid at the H2O, but then she adds the H, and that's the part I'm confused about. Like I get the whole like going from the like a 2 to 3 carbon cation because like it's more stable the more substituents, right? So I get that, like I can work with that, but my
This is
brain,
an acid. This is an acid, which means it's gonna give up. It's gonna give this up. And you gotta, whoops.
that's where that's H is coming from.
Yeah, this is like a stabilizer, right? This is like your intermediate where you're gonna get hydrogens from. So when you see H2O, just know you're adding. This is a hydration reaction across the molecule, but you need to like. There's nothing. This isn't gonna interact with anything, right? Because it's like it's happy on its own. So we need something. So we need this base, right? We need this base to be able to like interact. So, excuse me. We need an acid to be able to interact with. So we're gonna take. So yeah. So if you see this, just automatically know you're starting with H3O. Period. This reaction, H3O is gonna start you off. Just like make that a rule in your head and don't forget it. H2O will come in later in the middle of the reaction, but at first you gotta like peel. You gotta peel this bond apart. You gotta peel whatever the bond is apart and get a cation somewhere. This you will always see a cation, right? Like, I mean, maybe I shouldn't say always, but 9 times out of 10, if you see it in this exam, and in these exams, is because they're trying to set up a cation so that they can see if you know that you're gonna have a shift, right? So just put it in your head. There's H3Os. It's because there's all these things going on, right? Just imagine, right? Because I used to think the same thing. Like, where the hell are you getting this other water molecule from, right? But like, these are always this is an aqueous solution, which means there's millions and millions and billions and trillions of all these molecules just like floating around everywhere, right? So you have like all these interactions that are happening between all these molecules, right? And like, and you know, this hydrogen's peeling, I mean, this oxygen's peeling this hydrogen off for a second, and then this is, you know, it's interacting over here and over there and blah, blah, blah. So just, yes. Okay, no problem, Avery. Oh, you already left, sorry. Okay, so just imagine that this is like a big mixed up bag of things, and it's like hydrogens are just like jumping around. Hydrogens have no loyalty. They are placeholders, and they like make things happen, right? They help like shift energy around. I keep telling Jackie, like, imagine that these hydrogens are like your ESA Pomeranian dog, right? They don't really mean anything. They're not gonna like do anything to like save you by any means, but they're there to like support you and like help things move along, right? So that's how you have to think of hydrogen. Like, think of hydrogen just as this like totally like polygamist type, you know, atom. I don't know how else to say it. So that's why. So if you see this, just automatically think H3O, boom, right off the bat, right? It's just make it a rule in your head. All right. So
Perfect. Okay, I like rules.
yeah, I know everybody likes rules, right? Just like H3O, boom. Like we're just okay. Oh, H2O and H2SO4, perfect. That's that, you know, H3O, great. So then we do this. Stupid. Okay, there we go. We do this, and then we get, and then you get your hydrogen, and you have your cation, excuse me. And then you also have now this no formal charged water, right? Just so that you can see what happens with this, right? So now you have a cation, so now what happens? Is that the most stable place for the cation to be?
No.
Where would it be? Where would it be happier?
On the carbon that's right to the left of it.
Mm-hmm. So what kind of a shift are we gonna have?
A hydrogen shift? What is it? A hydro or something shift?
Not a hydro shift. Look at your, that's what's nice about these problems. Don't get too used to it because you're gonna have to create your own.
Oh, a
Create your
methyl
own.
shift, because
Yeah.
one of the methyl groups to add on to the cation and like kind of switch it, right?
That's right. And look at this, right? We're not going to put this hydrogen. We're not going to put one of these hydrogens here, first of all, on this one, because the cation will never want to be on a terminal carbon, right? So that one's already out of the way. This, 1, 2, 3, this has one hydrogen on it already. Okay. So this is now, so the only other option would be to look at the one right next to it, and we see that this one has 4. So, and there's 0, there's no hydrogen on this one. So it's going to have to be, right, a methyl shift. Does that make sense? So then we do that. And
Sorry, wait, can I jump in here for a second?
always.
Because yeah, I think I'm like a little bit behind what you're explaining in terms of like understanding,
Okay.
in the sense that yeah, I don't have the intuition for like where the hydrogen would attach. Like, how did you make that original decision that it's going to go on the terminal carbon and then the cation part would be in the middle? Like, can you just explain like how you knew that?
Because where are, sorry, my in-laws they just arrived. So if you hear my dogs bark in the background. Right, we're building concepts. Okay, got to think about this as building concepts. So where was the double bond again? It was here. It's a terminal carbon. Right. So if we break, right. So do you remember this part? Do you remember what I just highlighted in green? You remember that?
I mean, yeah, like I remember like what was said during lecture. I just
yeah, we'll get there. These are rules. You like rules, right? Your rules are that increasing. Hang on. Did it go away for you?
Yeah, it's a black screen.
I know, so annoying. There we go. Okay, it's back, right?
Yeah.
Okay, cool. So remember, we like rules. Everybody likes rules. This is a rule. Your methyl, this is increasing reactivity, aka decreasing stability, right? Increasing stability or decreasing energy. So the more stabilized, the more friends you can think about an anion as a radical. Remember? Radical thinking, the more friends that are around it, the more stable the radical is. Remember we talked about this? Notice how, yeah, go ahead.
Wait, isn't that just like saying like it's more substituted, therefore it's more stable?
Yep.
Yeah, I know that part.
Okay. So, okay, just pause, wait. So you know that part. You know that the more substituted a radical or a anion is, same thing, we can think about it the same way, right? The more substituted it is, the more stable it is. Now, if we are going to break this bond here, right? We're going to break this bond here, this pi bond, okay? So we're going to create this new, and we have a choice. We can either put the cation here or the cation here. The cation has to go somewhere. All we're doing is attaching a hydrogen at first, one step at a time, right? So the cation has to go somewhere. So with this in mind, this green, right? With this in mind, what we have is this is a methyl, B is a methyl, and A is a secondary. So with that in mind, where would a cation, remember we want lowest energy possible. Where would the cation be the most stable?
Yeah, so it'd be on the 2 because it's a 2 substituted, whereas the other one has 0 substituted, given that they're all hydrogen.
Yep. Secondary, right? Secondary cation. Yep. Yeah. Exactly.
Okay.
Does that help?
Yeah.
Perfect. Okay, cool. Yeah, it's just wherever you're breaking. Yeah, you're welcome. It's just wherever you're going to be breaking the bond. Whoops, I forgot we're up here more. Here we go. Okay, so we're back to here. Now you don't have to draw that hydrogen. I'm just doing it so you can see that it doesn't disappear, but you really, you don't have to draw it. So, whoops. Okay, so now we're doing a methyl shift, and I always like to write methyl shift just so it's super uber clear. I don't know if she makes you do it, but I do it just to make sure we all know, right? And
So
so
how do you know you're doing a methyl shift, or why are you doing that?
Okay, so for this is our reactants, and this is why I highlighted it. Rearrange cation intermediate. This will have a cation intermediate. These ones will have a cation intermediate. Now it says rearrangements are possible because your cation might be on the most stable carbon. It might have the most stable position when it is formed. So you might not actually have to move the cation, but you will have a cation with these, right? So HCl, CCl4, and H2O, H2SO4, and heat, right?
Yeah, just one thing. What does that notation mean? I don't get it. Like HCl/CCl4. Is that just saying that the CCl4 is your solvent?
Mm-hmm.
Or like what is reacting with what exactly?
You're going to be reacting with this. Same thing with this. This is going to be your reactant. And this is just, and you need heat because this is not a strong enough reaction. Excuse me, a strong enough reaction.
So, for example, for the first one, you have that hexane, whatever, that hexane of sorts, and that's going to be reacting with the hydrochloric acid and the CCl4. They're all reactants?
Isn't it a reagent? 2 reagents.
Yeah.
Yeah, but I mean, they're all going to be reacting together on the left side of the equation. Is that right?
I mean, like,
I just don't understand how to read, you start with that hexane and then are we reacting it with everything that's above the arrowhead or?
Yeah, so like these are always going to be your reagents that you're not. This is kind of just what pushes it along. This one, as you're going along with it, you don't have to, you'll just kind of know, right, how to do those. I'm trying to, let me just, I'm looking in the book right now just to see if I can bring up an example for you.
I know that in her Zoom.
Yeah.
In Zoom, extra credit Zoom, it's 11 C and D that use the 2 reagents. So if you wanna.
Okay, yeah, thank you. I have to do that later. I didn't look at that yet.
11 C and D. Is that what's 11 C and oh you mean in the extra credit?
Yeah. Question 11
okay.
C and D do use the 2 reagents. So if you want to look at that one after.
Got it. Okay, yeah. Okay, sorry. I didn't understand what you're saying. But yeah, so it's gonna, break across the bond to be able to pick up the CO, right? So cation intermediate. So with this bond would break, it would pick this up. The hydrogen would go here. The cation would go here, and then this becomes negatively charged, and so then it would react with that. This we wouldn't have a shift because it's already on the most stable, right? So we wouldn't have a shift, and that's how we'd end up with this over here. Right, so we pick up the hydrogen first. Yeah,
so where is the CCl4 or CL4 involved? That's what I'm not understanding.
So with this one, I'm not exactly sure how, because I don't want to tell you exactly how the mechanism of that one works with like this example, because I'm not positive how this necessarily supports this reaction. But I know that a lot of these have to do with like just being able to like support whatever's happening within that, right? So like, okay, so like this, you know, it might be like where this pulls this off, right? But then this is here. So then it, what's it called when it's a, like a catalyst, that's the word I'm trying to think
Yeah,
of. Jeez
I
Louise.
yeah.
And then you
No,
regenerate your
yeah.
catalyst. Yeah, go ahead, sorry.
Yeah, I hear you and I get that. I guess my confusion is just I don't know what to expect that's going to be represented in the product. So you see how in the product, the only thing that's on there is a chlorine? Well, like, how do you know that like the CCl4 is in essence disappearing and that we don't have to like show it in the product as well as the hydrogen on the hydrochloric acid? Like they're not there.
How would you
And
put,
I don't know
you
how
couldn't
to.
put CCl4 on it. Like it's not, you mean, how do you know it's not going to be this?
I just don't really
Is that what you mean?
understand. Like everything seems so like arbitrary to me. I just don't have any intuition for like what we're adding onto our reactant. Like
It's only
where is
gonna-
the hydrogen in hydrochloric acid? Like where is that?
Right here,
But I mean, where is it on the product?
right here.
So just because it's not drawn, then it's still
Yes,
but
exactly.
nothing in the CCl4 is on there. That's just something that's in the intermediate
Catalyst.
in the mechanism.
It's just a catalyst. It helps to like move the just like how heat, right? In this case, you know, you could say that, but right, it just helps to move the reaction along.
Okay, so you're saying for the first two, the rearrangements are possible due to trying to find the most stable position for the positive charge. Is that right?
Yes, exactly. Yes, because you
Okay.
need to, yeah, you need
Okay.
to have a stable cation. In this class, it specifically says in your in the gap notes, it specifically says to if a cation can be shifted to a more stable position, you will automatically assume that in this class. It specifically says it in your notes, right? So there may be, you know, things down the road that you might see in other classes where you wouldn't necessarily put it on there, but you do in this class, like where you wouldn't necessarily move the cation around, but you do in this class. You just assume that if there is a carbon next to it where the cation would be more stable. Yes, okay, no problem. Yeah. Yes, okay. Like, does this help you move along, Miriam? Like, you know, we do our methyl shift and then we've got our positive here. Whoops.
Yeah, it was just really where the H was coming from, because like if I don't know something, I can't just assume it's gonna like I'm gonna be good all the time. Like the first
Yeah.
was like really confusing. So I know the rest, like moving the positive towards a more substituted area and like having it to be more stable, right? So that the what's it called? What is it? The HO or will get attached to there instead, right? So
Yeah, so then this, so then we have our H2O. This is where our H2O finally comes in, right? And this is how we're gonna get that. And this is the hydrogen that we're dragging along with it, Jackie. And we can go back over this again, but right. And so now we have our H2O. So now this is where another H2O comes in and takes the hydrogen because this currently has a positive charge, and you know, oxygen doesn't like to have a positive charge. So it will take that, which will then get us over here. And then we'll have an H3O that'll go and react with something else, right? So that's how we get the H3O in the first place, is by peeling it off of this intermediate. Does that make sense?
oh right, because it's like going in a cycle basically.
Yeah, exactly. So then this H3O will just come around and attack another one. And that's, see this H3O right here, right? and it'll just start the cycle all over again until you come to some sort of equilibrium.
Okay, one last thing. So that basically my mind goes like, okay, I see the HO, like what is the way I can get to the product? Like what way can I go from here to here, basically? And so when I do get to there, because it's so many steps, so how would the transition look like?
Yeah. So, what do you mean? How would the transition look like as far as like
'Cause this one
moving?
has-
Yeah, go
Yeah,
ahead.
because this one has like 3 intermediates and 4 steps, right? Like 4 transition
Mhm.
states. So then, like it wants to, it asks us to make sure to do a to do
Energy diagram.
not the energy diagram, but what is it called when you draw like the skeleton of it? Like,
Oh yeah. The oh gosh. Yeah, I know what you're talking about. I can't think of it
doesn't
right
it
now.
ask that in number
I
10?
don't
Does
think this one does. Does it ask for it? Let me see. Draw a full reaction energy diagram. Oh, number the transition states. No. No, because you know why this one doesn't ask is because you'd have a shift. Some sort like this one has a hydride shift and the other one has and B has a methyl shift, right? So it doesn't ask for whatever the heck it's called. What the heck is it called? Transition state. Identify the partial bonds.
I
They're
keep thinking
transition
of it
states,
as
but
a transition state, but the
they are, but so it asks for the number of transition states associated with the mechanism. So it doesn't ask you to actually draw out the transition states, right? Because there would be, that's what these are. Transition state 1, transition state 2, transit. So if you actually drew it out, you know, that's what these would
so
look like.
messy, right? Because it's so many
Yeah.
different. Okay, so if I see like cation stuff, like the whole like shifts, just know there's not going to be like a drawing of the transition state then.
I'm not saying that. I'm saying that if this one, it specifically asks to number the transition states associated versus this one says to draw the transition state. Do you see the difference there?
Yes.
Draw the transition state versus number of transition states, right? So
Yeah.
just read the question carefully.
Is it so since we like worked it out together in the extra credit, and so it seems like, oh, like since she's doing it right in front of me, it makes sense. But then like if I look at it the test, nobody's gonna do it in front of me, so it might not make sense. Is it okay if you give us like examples and like you don't really have to necessarily work them out, just because she said to make sure you practice on that everything is gonna be the same on the test, but it's just the structure of the alkene that's gonna change. Is it okay if we give us like different structures of alkenes that we can practice on, possibly?
You mean me specifically? Yes, let me see. So let me look in this energy diagram section of the homework. Have you done the homework site yet?
Yes and no.
Okay. I will tell you from experience, do homework practice problems. So because they will help you immensely.
Which category is this?
So this one is might be energy. I'm looking right now. This one might be energy diagrams, but it also let me see. It curved arrow mechanism. This one's probably mechanism actually. I'm trying to look right now. Yeah, there's some good examples here. Draw a reaction diagram corresponding with that one.
So the ones where they have you draw it is like in the last part of the part 1. But in terms
Yeah.
of the mechanisms that are in the part 1 questions, they were easier. They were just like kind of figuring out how to do your curved arrow pushing to like get to the product that they said it was. The ones that you have to pretty much do from scratch that are in the part 2 section are the ones that are the last 2 problem sets of part 2.
Yeah, so it looks like the last two problem sets of part 2. So I'm in organic reactions. Like if you go through after summer practice exam 3, there's organic reactions and alkenes. Oh, alkene 1 reagents, alkene 1 reactions. Let's see.
That one is the one that I am having a hard time with too.
Yeah, I would say practice those. Alkene 1 reactions and alkene 1 reagents. Those look like good problems to try as far as like, but they don't even give you the product, which is like even better for practicing, not for like figuring it out, but and then let me see what reagents say. Oh, and then that's like guessing what the reagent would be. Yeah, so Miriam, I would say practice reactions and then you could practice reagents. That would help you kind of piece the two together. I think those would probably be, that would be my suggestion. You know, it sounds like Jackie wants to practice them too, so you're welcome to stay on and practice some of those. I can pull some off the homework site. Jackie, is that what you were going to ask to do today?
Yeah, honestly, I'm just feeling like stressed because for the part 2 content,
Alkenes?
I don't feel good about it. So I was hoping maybe we could go through the content first to make sure to kind of figure out where I'm missing something. So if you could maybe just start on like page 5 and then like we go through content, I think that would be like helpful.
Yes. So as you know, I just kind of pull sections out, and I don't necessarily always have it all. So I will do my best to like be able to have this up here. Miriam, feel free to hop in anytime if you have more questions, or if there's if you're looking at the homework and you see something that you want us to practice together, I'm happy to do that with you as well. Okay, so here's alkene stabilities.
Yeah, so I'm fine with that part.
Okay.
So starting at like where it says addition of the
right here.
HBr and HCl, yeah.
Yeah.
So okay, I guess this is the start of the rules. So I just want to make sure. So what these examples are getting at
content this week.
Yeah. So is it like what these are getting at is that you add the like group 7 like element to whatever is the most substituted and the hydrogen goes to the least. That's what I took from this. Is that all that they're trying to get at?
Well, so as you can see, right, there's major products and minor products, right? So we have both, right?
Yeah.
We do have both. But your major products are going to be where your hydrogen is your
like heavier atomic size. Is it that the heavier atomic, like the one with the more priority goes towards the more substituent?
Stable. Yeah, the more stable. Yeah.
And I guess wait, is this the principle you were just saying before, how like the positive charge goes on the more substituted? That's the point about the 3' or whatever it's called. Tertiary.
Yeah, tertiary, yeah. Or third degree cation. Yeah.
Yeah.
Yep,
Okay.
exactly.
So I get
so this is as you see Markovnikov, right? So this is the start of where you're gonna see this stuff, right? Markovnikov and anti-Markovnikov, right? So Markovnikov means that you're getting that's going to be your major product. It's the more stable product, right? So that's why your major product, the more stable product, is going to be the bromine on the more substituted versus less.
And then like in the next example with the hydrochloric acid, so I see like we took the electrons out of the pi bond, and then you put your hydrogen on the terminal carbon. Is that just like kind of something that we should like expect to, tend to do? Hydrogen goes on terminal and then the chlorine will go on that substituted cation.
Yeah, because again, remember this has to do with the fact, I'm just going to draw it out real quick because I didn't copy it because it's just the same content, right? But because remember, this has to do with the fact that you want, like, your major product is going to be Markovnikov. It's going to be the more stable, right? And so this is where you're going to be able to start to see HCl, right? And this CCl4 is just it's your inert salt. It's your solvent, your inert solvent, right? It's just what helps kind of make things go along. But yeah, so you're going to, that's just part of the nucleophilic or electrophilic addition, is that you are going to have the most stable intermediate as it's going to be the fastest, so it's going to be your major product. So when you peel this pi bond apart, you're either going to have here, or you're going to have, whoops, I should have done this, or you're going to have here, right? And because B is the more stable of the two, you're going to have the majority of your product be here, which means that your CL is going to go here, right? So that has entirely to do with the excuse me, stability of your cation.
Okay, yeah, so on that point, so when we're looking at the minor side product,
Mm-hmm.
I don't understand how the positive charge got to the far left of the molecule.
This B?
No, like from the filled out notes.
Up here?
Uh,
Is this what you're talking about?
no, it was the same example that you were doing. It's like in the notes that like they put on Canvas, like in the PDF of like the completed gap notes.
Yeah.
They drew the major product like the way you did, and then for the minor side product, they have the hydrogen and the chlorine in reverse, you know,
Yeah,
so
flip
like
flop.
they, yeah, and then the positive charge is on the far left of the molecule. How is that?
Wait, you mean there's a formal charge on the product?
I mean, they have a plus sign on the far left. I don't know if that was
No,
intended.
no. It's and this product. Not like what they're saying is like they have this product and
Oh, are you sure? Because I don't know, because like it's inside the parentheses. That's why.
yeah, because what they're saying is like you also have this product. This is your minor. That's what they're trying to say. It's not
Okay.
that like it would be a formal charge if there was a circle around it.
Okay.
Yeah.
Okay.
That's what they mean by that.
So then I think I feel fine with this section. And then if we keep going, it's like, yeah, so now they start talking about the stereo specific stuff.
Yeah. That's this right
And
here.
yeah, exactly. Yeah, so like I guess like do you just like how do you know where you're adding things? I guess this is like the part I'm confused about. They just put in a hydrogen, they just picked one of the methyl groups to like attach a hydrogen to one of those carbons. So they just made an arbitrary choice, is that right? And then
Yeah, it could have gone to the other side.
from there they just added the bromine. Like
Yeah, go ahead.
I just want to make sure like
So this is step 1, step 2, right? And this is also step 2, right? It's just we've turned it sideways, right?
yeah,
Equal.
yeah.
And then step 3, right? Because this is our transition state, right? And then here's number 3.
So,
in their products.
so like it says because there's a mixture, the reaction is not stereo specific. So then what would need to be different for it to be stereo specific? I just don't.
Yeah. So with this one, the bromine can attack from both the top and the bottom. So because if you try to think about this as far as like 3D-ish, right? This is a planar. That's what this is trying to say. Like this is planar. So that means that this methyl, all right, let me just change. This methyl is on the same plane as these carbons.
Yeah.
Oh, boy. Okay. So
I think I understand. So it's like saying you can get the two different like isomers because it's like the different orientation in space, right?
yeah. So we're we're in this plane, right? That's kind of a shitty plane, but I hopefully you get what I'm saying. And so because this is planar, this is planar, right? The bromine can come from the top or the bottom. Now, if it wasn't, as you'll see later on, we have some that are stereospecific. But for this one, it can go either way. And this one over here is no longer planar because we attached a hydrogen to it, right? See this hydrogen here? So that this means that due to electron repulsion, it's sp4 or sp3 with 4 electron domains. Jeez Louise.
Yeah, I see. Okay.
Cool.
Okay, the next one I was hoping you could explain because I don't understand for the carbocation rearrangement. My difficulty with this is so in their first diagram, I was looking at like the one above that, but
no, I know. I just
sorry.
didn't copy it in here, but you're fine. I have my own notes that I can follow along with you. So,
Okay.
For anybody that listens later on, we're on page 7 and 8 of
Okay,
alkenes.
What I don't understand about this is so they're breaking the pi bond, and so now making a bond with the hydrogen in hydrobromic acid, I guess is how that's called. So, okay, and then I believe that that hydrogen is what's being added to the terminal carbon. Is that correct?
No, okay, so let me draw this out. All right. I'm gonna draw out our structure.
Okay.
Okay. I was hoping I could make it a little bit smaller because, of course, I wrote too big. That's right. I just want to do out the full reaction. They can see, you can see. Okay, and then I'm going to draw the HBr up here. Okay. Does this look safe so far?
Yeah, that's what
Perfect.
they have.
Yep. So what we're going to do is we have this double bond that's going to react in the that's going to be included in the reactions, right? That's how we're going to get things moving. Okay. This is an alkene chapter, right? So we're looking for the alkenes, right? So got it. Okay. Yeah, no, I'm just breaking it down one at a time here, right? So we have a hydrogen here. We have 2 hydrogen here. Okay. So far, so good?
Yep.
Okay. So when we break the bond, we can either go this way or we could go this way. Okay. and I'm going to do these in 2 different colors. If we go this way, if we go this way, we're pointing at where the bond's going to be. So it's going to be here, right? And if we go this way, we're pointing at where the bond's going to be. So it's going to be here, right, to the hydrogen, right? So far, so good?
Right. Yeah.
Okay. So now for, oops, conversation's sake, right? Because we know that this is just a funnel,
Yeah.
right? Okay, cool. So 1, 2, 3. 1, 2, 3. 1, 2, 3. Right. And I'm
Right.
doing this just because it's just good to be thorough, because there's been many times where I've missed a carbon or put too many in, right? So
Yeah.
we have an option to do, a cation here. I should have kept it the same. So we have an option to do our cation here, which is this blue, right? Or we have the option to do our cation here, which is this, whoops, other way around. Sorry, friend. Right? Because the cation would be in opposite of where the bond is. Does that make sense?
Yeah.
Okay, cool. So far, so good. Right? These are our 2,
Yeah.
this is 2 options in one, right? Hopefully that part is clear. And I just want to say that for
Yeah.
if anybody listens on.
So you would take the yellow one because it's more, that carbon is more substituted.
Yeah, so that would be your major product, right? So
Right.
if we, yeah, so if we wanted to keep the yellow or orange cation, that means that our product would look like 1, 2, 3, and then we would write our hydrogen here. And then we also have from before, right, these hydrogen, right? These are these hydrogen.
And
Make sense?
the hydrogen that is on the, like the other hydrogen in, that's in like in the drawing. So if you count from the right, you had like the terminal one, and then there's the top peak, bottom peak, and then there's that other hydrogen. Is that just drawn in? Like, I don't know what that purpose that one serves.
Which one? These here? These purple ones?
Like, do you see in the structure that's labeled the secondary cation there, how there's 2 hydrogens labeled on there in red?
Are you talking about this down here?
No, in the problem we're on,
I just
like,
have my own gap note, so it's not in red for me.
oh,
Oh, are you talking about what would be, ignore the purple ones, but what would be this orange hydrogen here? Is that
so
what you're talking about?
there's that one, and then there's also one that's bonded to the carbon that's right next to the plus and
To
orange.
the left of the cation, correct?
Yeah,
You're talking
right.
about this.
Correct, yeah.
Okay, so technically there's 2 there. The reason why you draw it is to show the hydride shift.
Yeah, so I don't know why we're doing a hydride shift.
For the, because, oh, got it. Resonance stabilized. We have resonance here.
We have resonance there.
So if we, so let me show you. Let me show you.
Yeah.
I know why you're confused now. So I'm gonna draw this back out. I'm gonna draw our phenyl group back out, right? Because I got rid of it for the sake of, but so now we have, oops. So our cation's there, but we're gonna do a hydride shift here, right? So far, so good. That's what
Yes.
that's what this would be. This would be that. Okay. So
Mhm.
now I'm going to erase this, and we're going to put our hydrogen here. That was this green hydrogen. No, let me put it in green, right? From here, right? This green hydrogen. Okay,
Right.
and so now we have a positive charge here. But look at what we have here. We have electrons that are willing to go over there to stabilize it.
But
So these
isn't the bromide going to attach where that cation is currently?
Yes, yes, but I'm just explaining to you why we're moving the hydrogen, why we're moving the cation. Because
Okay.
remember, we're just trying to create a more stable cation, right? You are
Okay.
right that is where the bromine will attack, but the cation is moving there because of the resonance from the benzene ring.
I see. Oh, okay.
Yes, because the bromine is not going to attack over here like on a benzene ring, right? Because ultimately this is the most stable configuration of the benzene ring, right? But the reason that the cation moves is because at first glance this is like, well, that's a secondary and that's a secondary, so why would we go anywhere, right? That's your question, right?
Yes, exactly.
Yeah. So the reason why is because if there was nothing for it to react with, if we didn't have a bromine that was, well, R, but whatever, if we didn't have a bromine waiting to attack that cation and the cation had to exist on its own, it would want to exist where this resonance was. Does
I
that
understand. Okay. I'm seeing it now. Yeah, thank you for going through that because I
Yes.
didn't pick up on that the first time at all.
Yes. Yes. No worries. No worries. No worries. Of course.
Okay.
Okay.
Okay, so then when you just scroll down, then they're just illustrating that the
Well, this is a different
hydrogen.
problem. This one right here, this mechanism problem.
Oh, I mean, yeah, I was talking about just like the
Sorry.
last thing they said. Yeah.
Yes.
So then they're
Okay.
just illustrating that like there's a partial bond on those two carbons, given that the hydrogen can exist in those two places at certain times during the reaction.
Yes. Yes.
Okay. Okay. All right, so basically the strategy is like, you know, transfer the hydrogen from your acid onto the base and then make the base into the most stable configuration, and you look at the most like you can like the two things you consider are resonance and like the number of substituted
Well,
atoms.
even resonance has to do with stability, right? Let me show you, right? Resonance stabilized. The most, right? If you're look at this, you're on the cation is one away from, right? It's allylic. It's an allylic carbon. Allylic carbons are going to be the most stable.
Wait, sorry, what does that mean again?
Allylic means it's basically one carbon away from a double bond.
Oh, okay.
Yep.
Okay.
Right. And so a phenyl group, obviously those your double bonds are all over the place, right? So I forgot where I put that, but it's up here. Your double bonds are all over the place. So okay, let me do that. Right. So your cation here, and this is the next carbon over, which is an allylic carbon. Right.
Okay. And in that next example, the one that you scrolled to a minute, yeah, that one. So then I just want to make sure. So then this is the similar case in that the reason we're doing a shift, the methyl shift in this case, is because you want to get your cation on the most like stable carbon, and you're trying to get it to the tertiary cation rather than secondary. That's like what makes you do the shift.
Yes. So this cation here has two choices. It can either go here on the red one, or it could go here on the yellow one. Those are the only two places that your cation could go.
Mhm.
So you say, what is the most stable between the yellow, the pink, and the red? What is the most stable, right? And so, whoopsies. So our most stable, we have a second degree, a second degree, and a third degree,
Yeah.
or secondary, tertiary. So that's when we would say, oh, okay, well, it would be happier to be on the tertiary, right? And I'm saying tertiary, yes, we have 4 here, but what I'm saying is like, if we, it would be you get what I'm saying?
Yeah, no, I get it. And then
Okay, cool.
in the energy diagram also,
Mhm.
can you explain how you know the relative height of each
You
of the
do,
three?
yeah, it's like, it's as far as like this, and this, or just like how far up, or would it look like that?
Yeah,
Or like, is
like
that what you mean?
how far
Don't,
up as well as
don't,
how deep the valley is.
I know. Listen, I wouldn't worry too much about all that. We're talking about relative energy. As long as if your reactants are higher energy than your products, and let's just say you have 2 transition states, wherever your rate determining step is, a lot of these, it's going to be your first, right? Wherever your rate determining step is, that one needs to be the highest. Then you go down some, and then you come up again for another one, and then you go down. And as long as you're, displaying that your reactants are higher than your products, and that your overall, right? Like,
Yeah.
this, you know what I'm saying? So like,
Yeah, I got the general trend under control. I just didn't know like
no, there's no
all those very
specifics.
nitpicky things.
No. There's no specifics as far as that is. As long as this is looking, you know what I'm saying? Like, as long as
Mhm.
as long as it's obvious that, as long as you're not doing one of these, right?
Yeah, I get you. Yeah.
That's a problem.
Okay.
Yeah. Okay, so then what we have, let's see, additional water. This is page 9, right?
Yeah. Yeah, so this is what you were explaining before, I believe.
Yeah. Yeah.
But I just want to make sure. So like at the bottom of page 9, when they're going through, when they have like the hydronium,
Yep.
you were saying you have a hydronium just because like it's an aqueous solution, so you're gonna have some hydronium ions in solution. Is that where that comes from?
Hydrogen or H3O plus is a stronger acid than H2O, right?
Yeah, no, I know that, but like where does it come from again? I think you said that to
Oh,
the other girl.
yes. So when you get right here, so right, this is a stronger, so we get this hydrogen from here, okay?
Right. Yeah.
And then we have our cation because we broke this bond, and our cation is going to go on the most substituted, right? Because it's a
Yes.
Markovnikov interaction. So we have our cation here. Well, good old water with its dipole, and really it's non-bonded electrons, but wants to be here. We'll get to the dipole after, but wants to be here. So we've made this bond right here. But now hydrogen is positive. I mean, now oxygen's positive, and oxygen ain't having any of that. So, but because of, right, we've got this, and hydrogen, well, I mean, yeah, hydrogen is, the unloyal friend that'll just, friend hop. There we go. Right. And so it'll come in and steal this because oxygen wants to get rid of that. Oxygen's like, take that hydrogen away from me because I just want those electrons. That's all I want. I don't want you, hydrogen. I want your electrons. Right. And so
Yeah.
then this O2 is like, oh, okay, why not? Bring it on, you know? And so then-
Okay, so wait, so that water, that second water that's introduced in step 3, well,
This one?
between steps 2 and 3, yeah. So that is just because we're in aqueous solution, because I didn't know where that came
It's
from either.
everywhere. Yep, it's everywhere. I went through the same thing. I'm like, how the hell did this water end up here? It's an aqueous solution. There's billions and trillions and trillions and trillions of water molecules all around.
Okay, I
Yeah.
see it
They,
now.
you
I
just
didn't-
hop, water can hop in the reaction anytime it wants. You don't have enough
Okay.
waters? Watch this. Watch this particle move around a little bit more, and then we'll find some more waters to interact with, right? Like they're just clanging all around in this liquid state.
Mhm.
Right? Just imagine you have, you know, right, all these waters that can just do all this interacting.
And
You
then
know.
you know with the like energy diagram that it's overall exothermic based on this mechanism, like without counting all of the bonds that are formed and broken. How do you know that just like right off the bat?
That it's exothermic.
Yeah.
So this is so the electron energy doesn't change, right? We started with a neutral, we ended with a neutral. And then if your products,
Oh,
your-
has more bonds. Is that what you're gonna
Yeah.
say?
yeah, the products have a lower energy state, right? Like they're all sigma bonds, right? So they're all in the lowest energy state.
Yeah.
And you've made just as many bonds, like you've broken and made, right? You know what I'm saying? So
Yeah,
like
yeah.
you're not making more bonds than you're breaking. If you made more bonds, then it would have to be endothermic. I mean, yeah, endothermic because you have to add energy to it.
Mm-hmm.
Does that make sense?
Yeah.
Oh, there. I was like, I thought I put it in there, but yeah. So your catalysts are, remember I was saying they're never used up, right? They're regenerated right here. Your H3O is regenerated at the end.
Yeah, I see that now. I was just confused with the like water thing, but that
Yeah,
now
you
you
just
explained it, it made
automatically
so much more
assume.
sense.
Yeah, okay, good. Good. What
And then they
else?
went through the catalyst. The catalyst was fine.
Okay. Yeah, those make sense. And
Yeah.
then what do we have? We've got all these mechanisms on 14. Let's see. These are just more mechanism stuff. Oxymercuration, HDOAC2. That's one of those, oh, I have that right here. This mechanism, right? These are your
Yeah.
stereospecific, this one.
So yeah, sorry, I'm like on like page 11 at the bottom.
Oh, yeah.
I just want to make sure. So when you have the H2SO4 underneath the arrow, then that's not going to appear within your mechanism. Is that right?
No, nope. It's just it's a catalyst. It literally says it right there, H2SO4 and then in parentheses cat. So it's entirely just a catalyst.
Okay, and then for this, yeah, so then this was kind of similar to the example that we did before with like the planar stuff. Okay.
Yep.
I think I get that one. And then what was okay, and then for the next one, how do you know when you're going to go from the like 4 carbon ring to
I
the pentane?
Yeah, I know. I was trying to like look over this before. Because yeah, I was a little bit confused about this one as well, and I couldn't remember. So, because it says which one actually wins. Like, is this going to be a hydride shift or is this going to be a methyl shift, right? And so because it says both win, right? Like, is it a hydride shift or is it a methyl shift? So but it's funny because the hydride shift would make it more stable. That's what I didn't understand. So, but it says probably actually both will occur. So if you're asked to give the product of the reaction, you would not know how to answer it because it would not be clear which rearrangement to do. However, this is a mechanism problem. The product is provided. So in this case, you know indirectly which rearrangement to do. It had to be a ring expansion in order to get the provided product. So that's the best explanation on that one. Because there's two options, right? You could do a hydride shift or you could do a methyl shift. Like either way, those would be correct, right? Either way, you're going to get a shift because there's either, it's either with a hydride shift, it would be a more stable cation, but a methyl shift is just as is also likely because it's still a second degree, right? But in this case, because they gave you, that's what's nice about these problems, these mechanism problems, is it gives you the product so you know what you're trying to look towards, you know?
Yeah.
So that would be my best answer for that one, because intuitively with the cation rule, it would be a hydride shift, but both could happen apparently.
It's just hard for me to see how to go from like the step 2. I just can't see that in my head, how they went from the 4 to the 5.
Yeah,
Like what attached to what?
the carbon number 5 attached to, if you started carbon 1 at the cation and then 2 at the beginning of the ring,
Mm-hmm.
and then 3 up, 4 to the left, 5 down,
Mm-hmm.
that carbon bond just shifted. It's a methyl shift, right? It's the equivalent to a methyl shift, an alkyl shift, right? Because remember, these things are making and breaking and moving, and electrons are like whirling around and things are happening, right?
Mm-hmm.
So I wouldn't get too hung up on this. I'm not gonna lie. Don't get too hung up on this particular problem. Take from this problem that they gave you a product and you have to find a way to make that product. And the only way to go from a 4 ring to a 5 ring is to do that alkyl shift.
Yeah. Okay.
That would be like my, like, as far as like what to take from this is just like looking at the product and looking at your reactants and like figuring out like how do you do that. Well, you have to open up the ring somehow, right? And an alkyl or a methyl or whatever shift, those things are allowed. You are allowed to have your carbon bond to that next carbon over, because it's close enough, right? You can't do it like 3 or 4 carbons down unless you were like it was allowed to shift in that way.
Yeah, there's just something I just want to clarify with the water and the hydronium. So going back to 11 on the bottom, the hydronium was introduced in step 1.
Yep.
Like, and then
11 at the bottom.
Oh yeah, like the
Oh
one
yeah,
we
I see
just
now.
did.
Yeah.
So the hydronium was introduced in step 1, and then in all the subsequent steps, it was just water that was being
Yes.
introduced.
Yes.
So I get that was like the convenient choice, given that like you're trying to get rid of the cation, but like, are you able to kind of just like arbitrarily like pick what you need, if that makes sense?
No, because you have to have the hydronium ion because it's a stronger acid, right? It can
I mean like
accept electrons
after
or
step
donate a
1.
proton. Yep, but then
I mean
after
like
that,
after step 1 though.
Yeah, but if you can't use a hydronium because a hydronium won't attach to a cation because a hydronium has a positive charge.
Yeah, but how do you know? Okay, okay, yeah, I see. Okay, never mind. Yeah, I
Okay.
get it.
Okay. Yeah. And then you need the hydrogen, you know, a hydronium won't do anything with any of these things except for breaking that double bond because you're dealing with electrons. All the other steps have to do with attaching either to a hydrogen, which means a proton essentially, or a cation, which is a positive charge, right? So all the other steps have to do with interacting with a positive charge, and you need an O2 molecule to do, or an H2O to do that because of the lone pairs and the lack of formal charge.
Okay. So with the whole rearrangement just in general, you have the possibility of rearrangement anytime you have a cation.
Yeah. Mhm. Yep. That's right.
Okay.
Specifically, like, and you'll see as you kind of start getting down into these, right? Is like you'll see that like we have a cation here, but we're not gonna do a rearrangement. What's gonna happen is this is like an example of like where you might not see that, right? Is you end up having this mercury, mercurium ion or whatever that kind of holds the place, right? And then you see this like you see these right partial bonds here. It's kind of a placeholder, right?
But how does that like triangular structure form from only the one pair, like one lone pair on Mercury? I don't get that.
Hang on 1 second. Okay, my headphones are like pulling my hair. Sorry. Okay, say that one more time. How does the triangular structure form what?
Yeah, so on that example you're on page 13,
Yep.
How there's like that triangular kind of,
Yep,
bond
this right here.
orientation. Yeah. Yeah, so the only lone pair is like the one that's on Mercury, so that would make one bond. So like where's the other one coming from?
Right here. Pi electrons, positive charge. That creates the first bond.
Yeah.
That's how you get this first bond here. But now you
Yeah, where's the other? Yeah, where does the other one come from?
Now you've created this cation, and there's a pair of lone pairs. Right? And so we have this kind of shift back and forth. Remember, this isn't a stable.
Oh, I am just dumb, I think.
No.
No, because I didn't know, because I literally did the shift from the double bond, and then I thought, oh yeah, I'm using up the lone pair, which makes, yeah, okay.
Yeah, you see you've got that formal charge here. Right? So you're gonna use a formal positive first. Yeah. Because listen, the other reason, right? Yeah, you're gonna use that, but also, right, when you're making, you've got to, you're breaking this bond here. You're breaking this bond. You're using these electrons in this bond. And so you can't use those electrons because.
No, yeah, I know. I just like, yeah. I don't know where that came from.
No, it's all good. I just wanted to point out why you wouldn't be using these electrons here because you're already using these electrons and you're only making one bond, right? So that's why.
Yeah, I see it. Okay.
All right. So now we got that. Let me see.
So okay. Yeah, so you for that example, you're gonna do that triangular thing. If like based on what? Like why would you do that first?
Well, you have to your mechanism starts with this, right? So you're going to make this connection to mercury at first. So what we're trying to do is we're trying to add water, right?
We're trying to add water. How do you know that? Oh, based on the above.
Yeah.
Yeah.
Whoops. Yeah, right here. We're adding water, but we're using this mercury, right, to do this. So, oops, I want to show you right here. So here's the difference, right? So we have a rearrangement. So that's why we use this, because the mercury helps from having a rearrangement, a hydride shift, a methyl shift, an alkyl shift, right? That's why we use the mercury. It's still Markovnikov, but there's no rearrangement, right? Like
So
this is go ahead.
So you want to avoid rearrangement? Because I thought rearrangement was just like a mechanism by which you can get a more stable structure.
It is, but you might want to make a product where you don't have rearrangement, right? Like what if you wanted to make a product that had a 4-membered ring? You'd have to use mercury in this case to do it, because otherwise you'll end up with some product. You'll have other products too. Like you'll still have, right? If you go this way, you're still going to have a product that has this, that would go there and this would go here, right? You'll still have this product, but it won't be as abundant. But if you're looking for this product in particular, you don't want to use this, because you're also going to get this product and it's going to be a waste. So say you even get 50-50, it's probably, you're going to get more of this one, obviously, but let's just say at best you get 50-50. Well, half your product you're going to throw away, because you're trying to get this one. Does that make sense?
Yeah.
So you'll see as we get further along. Right now, we're just trying to introduce reagents and reactant, and show you reactions and mechanisms, because later on down the road you're going to be doing synthesis and you're going to want to know how to create a certain product. Hey Arius, you're back. Got another question about something?
Yeah, I'm just a little bit lost on or like I guess I just going over like one problem about energy diagrams would help.
Yeah. Okay. Like this, for example.
Yeah.
Okay, what about this do you have a question about? Like what specifically about energy diagrams are you having trips up on?
Honestly, I just think like going over it, like the entire thing would help.
Yeah, like how to draw it.
Yeah, and like just like the steps, I guess.
Sure. Let's go to this, which is for the extra credit. So are you good with how we got to the product? Or do you want to do the whole mechanism too?
Yeah, I think doing the whole mechanism.
Sure. Yep. Okay, perfect. No problem. All right. Okay. So, like I had said, I don't know if you were here for it, but anytime you have this reactant, know that you're going to start with H3O plus first, because it's a better acid. Okay. So just automatically, I'll just make it a rule in your head. You see H2O, H2SO4, you're starting with a hydride. Okay. So we break this, right? We break this bond. And we want to put whoops, I did that the wrong way. We want to put the hydrogen, we want to have the cation to be on the most stable. So we have this, and then I'm drawing the hydrogen in that we just put on there, right? And then we're going to do what's called a methyl shift. We're going to take this methyl and we're going to put it on this cation. Okay. And I usually write methyl shift just so it's clear. I don't know if she requires it, but I usually write it on there just so we're not confused. So then now we've got this, right? And again, for completion's sake, here's our hydrogen that we've been carrying along with us the whole time, right? And, you know, this is a single bond, so there's 360-degree rotation, so we can put that methyl anywhere, right? So I did this because this is eventually how it would end up being. It's a planar, excuse me, it would be planar. Okay, so then we go, sorry, here's the cation, okay, and then we would have oxygen attacking this cation. So now from here on out, it's just our water, right? So we'd have our, and then we would get, our next product would be, right? And I'll draw this hydrogen off. You could drop that hydrogen off at any point though. You don't have to keep drawing it. It's assumed, okay? We're gonna do this. And now this is a positively charged, but oxygen doesn't like to be positively charged. It gets real angry about it. Okay, so these lone electrons are gonna pick up this hydrogen, which is going to in turn give us this product, plus, like any good catalyst, let me move this plus sign. Any good catalyst, it gets regenerated, right?
Yeah.
We're back to that. Okay, so there's our mechanism. So we've got transition state 1, transition state 2, transition state 3, transition state 4. Then we have, I'll do in a different color, intermediate 1, intermediate 2, intermediate 3. Your intermediates are always going to be your transition state -1, right? And here's your reactant, and here's your product, right? So now your so your product is going to be lower than energy than your reactants, right? So your reactant's gonna, you know, be somewhere up in here. So we have 1, 2, 3, 4 transition states. And this is gonna be your rate determining step right here, right? So however fast it can do this will be, you know, how fast the rest of these can go, because if we don't have this product, none of this other stuff is happening. So that will be our, so then so for every transition state, we need a peak, right? So there's 1, 2, 3, 4. It's okay if it goes off a little bit. I have kind of large handwriting, so that's why that happens. So then to be consistent with my colors, TS1, TS2, TS3, TS4, mother trucker, reactant, intermediate 1, intermediate 2, intermediate 3, product, right? And then it usually also asks for activation energy. It's really, like, really, if we wanted to be like super technical, this should be below this, right? Because our intermediate needs to be lower in energy. But anyway, so this is our activation energy. This is isothermicity, because it's losing energy from product to reactants. Does that make sense?
Sort of. How do you know that the reactants are higher in energy than the products?
Well, in this case, you have 1, 2, 3, 4 sigma bonds, 5 sigma bonds, excuse me, 5 sigma bonds and 1 pi bond. And in this one, we have 1, 2, 3, 4, 5, 6 sigma bonds, not including our hydrogens, right? But just our carbon-carbon bonds or carbon-oxygen bonds or whatever, right? And remember, sigma bonds are lower in energy than pi bonds.
Okay.
Okay.
I'm a little bit confused on like just like how we make the transition states. Like, to be honest.
You mean like on the energy diagram?
No, like how like how we come to like make
In
them.
this case, your transition states are the arrows. So it's whatever's happening, like, but if you're gonna draw a transition state, right? Let's take these two, for example. We want to draw what our transition state is. We need to draw, and you're not gonna do this for this, but we need to draw our, sorry. We need to draw our skeleton, okay? And then there's this carbon here, right? That's also a part of it. And so we have this, right? And then overall, our transition, oops. Overall, our transition state is positive, which I think we actually are supposed to drop. Maybe, is it below it or something? Whatever, anyway. Overall, our transition state is positive regardless, because we have a positive charge here and a positive charge here, right? So this is the transition state number 2. Okay, that's what that transition state looks like. But you're not asked to draw the transition states in this example. These just want to know, like, what does your energy diagrams look like, right? This transition state would look like this. Excuse me, draw your skeleton. I'm not drawing this because it's just, draw your skeleton, and then, right, and that would be your transition state there, because this bond is being broken and this bond is being made, right? So that's what your transition state would look like for this one.
And if you don't need to draw the transition states, then like how else do we know that there are 3 transition states?
Because of your arrows.
Oh, wait.
1, 2, 3, 4. Got to get there somehow.
Wait, will you do that again? I think it was like lagging. Sorry.
That's okay. Can you see the purple highlighter? Oh, I see. It is lagging a little bit, huh? Come on, get with the program here. Let me know when it comes back up.
I might be able to see it. I'm not sure.
Hang on. I don't see it on my screen.
Yeah, I don't see it either.
Did you see that pink line I just drew?
No.
Let me stop sharing for a second. I'm gonna reshare. Hi, Jasmine. Okay, here we go. Perfect. So these are your transition states, your arrows. Okay. You don't have to draw them out because she doesn't ask for it, right? The number of transition states versus, maybe it's further down, versus draw the transition states, right? That's when we draw the transition state. But for those energy diagram questions, you don't have to draw the energy. You don't have to draw the transition states. You just have to know how many there are. Most of the time, it's going to be however many arrows you have. The only difference would be is if you had structures with resonance. Remember, you have this structure, and then you have this structure, right?
Mhm.
This would just be considered one intermediate, right? It wouldn't be two intermediates, right? One and two, right? This would just be considered one intermediate. I don't think you guys have run into this yet. Maybe you have, but
Okay.
does that make sense? So that's why we have these, that's why we have these 4 transition states.
I guess I'm a little confused on like drawing the actual transition states then.
Okay, sure. So if you have boop, and then we get, right, with, I'm just going to do this because it's implied, right? But our transition state would be, you start with your skeleton, right? So what are 2 things here? Let me draw this too. Okay, that'll help make it more clear. This is just like a super simple example, right? So let me get rid of this so I have more space. Okay, so what are some things that are in both structures, right? So we have structure A and we have structure B. Okay. Well, and this isn't totally complete, right? There we go. That's correct. Okay. So some things that we have that are the same is we have 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. Okay, so those are the same. So we can draw 4 carbons. 1, 2, 3, 4, right? What else is the same? We also have an H, right? We have an H here and we have an H here. And then we also have a Cl. Those are also the same, right? And so we have a Cl. And the Cl technically has 3 sets of non-bonding electrons in both cases, right? So then our transition state would be the breaking of one bond and the, let me do a different color, and the making of another bond. So we've made this one and we've broken this one.
How did you break that one?
Oh, I didn't draw the curved arrow, sorry.
Oh, okay.
Sorry about that.
Okay.
Right. And there's no charge because there's a negative and a positive, so cancels out, and this is neutral, right? So there's no charge on this transition state. Does that make sense?
Yeah, and then when the reactants are higher than the products, that's exothermic, right?
When the reactants are more energetic than the products, that is exothermic. You are releasing energy to make the product. If the product is higher in energy, i.e. you've made double bonds or whatever, you make more bonds than you broke, right? Then it is endothermic. You have to put energy into it.
Okay.
So think like endo is like endothermic. You have to put energy into it. Endothermic versus like exit. Energy's exiting, right?
Okay. All right. Thank you so much.
You're welcome, Avery. No problem. Okay, Jackie, I'll give you one more question because my in-laws have been here and I would be happy to continue to stay on, but I do want to visit with the family for a little bit. So I thank you for your patience with everything. But if you could pick
It's
one
okay.
more
I was just
thing
gonna say, I know
to
you've
work
been
on.
here forever. So
No, it's okay. It's okay. If you could pick one more thing to work on, at a, what would you want to look at before we get off?
Yeah. Okay. My last one, yeah, is if you could just go to page 17.
Okay.
This is a quick question.
Yeah.
I think it should be at least
Look at 17. Okay. Yep. BH3 right
because
here.
it's like important.
Mhm.
I truly just don't know how to read the arrows in the sense of on top of the arrows, it has BF3 and then the THF. I thought we said that what's on top of the arrow like shows up in the product and like what's on the
Mm,
bottom of the arrow is like the
mhm.
reagent. I mean, is
Yeah,
the catalyst. But
I know.
like
This is the one
I don't
exception
know.
to the rule.
I just like don't even know by looking at the arrows anymore what the reaction is. Like I don't know if I'm supposed to be using BF3. I don't know if I'm supposed to be
Everything.
using OH.
I know. Okay. So if you go back one page to page 16, right? BH3 THF this is like a multi-step reaction. The thing to look at here is that you're using peroxide, hydrogen peroxide, which means that it's going to be anti-Markovnikov, right? Oh, these are like stereo specific. But yeah, it's anti-Markovnikov anyway. If you look at the top one, I was looking at these bottom
What
ones
does
here.
that mean exactly? Anti-Markov?
Markovnikov, anti-Markovnikov. All that Markovnikov is some chemist, right? And Markovnikov means that the cation, or rather the water that you're adding, which is the OH, but the OH will go on if it's Markovnikov, which is your like HBr and all that, HCl. If it's Markovnikov, the OH will be attached to the most substituted carbon of the double bond that you're breaking. If it's anti-Markovnikov, which will be anything with peroxide, like in this example, where is it? Further down, right? Right here, peroxide, right? So we're using peroxide to add, really what we're doing is we're adding this OH here. This is the OH that we're adding, right? But when you see peroxide, that just is like automatically, this is anti-Markovnikov, which means that it's going to the least, see how this OH went to the least substituted of these two carbons?
Yeah,
When you're
how do you
breaking
know
it,
it's going to be anti?
because that's just the rule.
Oh,
If
is
you
there
see
another
this,
rule? Yeah.
if you see
Is that the
that
only
BH3
rule?
for the anti-Markovnikovs,
Yeah.
there is, let me see, I put the reaction summary table in here.
Okay, I just will look at that then.
Yeah, so let's see. Oh, it doesn't actually say it in there. Okay, so let me write down some things in here that were helpful to me that I wrote in my own notebook, right? Let me just get rid of this. Okay. So some things that were helpful to know is that this, which was also equivalent H, there we go. HBr, right? HI, right? Those ones. Okay, this is Markovnikov. Okay, so it means it's going to go to the most substituted.
Yeah.
Okay, this, this one, right? So both of these, right? Rearrangements are possible. This one is also Markovnikov with a rearrangement, right? These two are kind of the same, right? You're probably gonna have a rearrangement, right? But the difference is with this, you're adding water, and with this, you're adding your hydride. right? That's the difference
Uh-huh.
here. But those
Got
are
it.
both Markovnikov with a cation rearrangement. Well, with a
Yeah.
cation intermediate that will probably be rearranged, right?
Yes.
This is anti-addition. This one is anti-addition. They're big molecules, right? These
Uh-huh.
are big, 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 big. They can't be on the same side because of electron repulsion. Okay.
Uh-huh.
This same thing, it will also be anti-addition. And it will be it'll be anti-addition, but we're adding an alcohol. ETOH. So we're trying to add the alcohol as if just like up here, right? We're trying to add here, we're adding the halogen, here we're adding the halogen, here we're adding an alcohol, and here we're adding an alcohol, right?
Yeah.
Hydration reaction, okay? So
Yeah.
these are Markovnikov with cation rearrangement, most likely. Cation with probably a rearrangement, right? This anti-addition, Br2CCl4, anti-addition of your halogens. With your alcohol, anti-addition with the halogen, but with the alcohol as well, whatever that is, right? Like
Uh-huh.
it's going to be OET because you have this ethanol, right?
Yeah.
Okay, cool. And this hydrogen is used to whatever, you get it. Okay, cool. This anti-Markovnikov automatically. So it just means that your there will be no rearrangement, and this is not stereospecific. I'm just gonna write it like that, okay?
Yeah.
No stereochemistry, right? There's no stereo, like it's not whatever.
Yeah.
This anti, oh, I'm sorry. Sorry. I was getting ahead of myself. Mercury is Markovnikov. Sorry, I was getting ahead of myself. Mercury is for sure Markovnikov. BH3 is anti-Markovnikov, okay?
Mm-hmm.
And it's syn addition, okay? Which means that it has to attack from the same side, okay? And then H2 is also syn addition, and there's no rearrangement, okay?
Yeah.
I hope you wrote those down.
Yes,
Those
I
are,
got it.
okay, perfect. Those are great ways to just think about these reactions. Those are like the quick and dirty, like this is how you will predict it.
Okay.
Okay.
You are the best, literally.
I got you. No problem. I'm trying to get in on OChem too, so we'll see what happens. So it's a different
That
professor.
happens in my life is great. That
We'll
doesn't
see what
happen,
happens.
and that doesn't happen, and I cry.
Yeah. Well, we'll see. I'm happy to keep doing it if I can, but we'll see what happens. So anyway, hopefully that was
Sarah,
helpful.
thank you.
Yes,
A million.
you got it. I know a lot of material to learn this week, but you got this, I promise.
Thank you. And I'm sorry for keeping you so long. Please go enjoy
No,
the
you're
in-laws.
fine. You're fine. No worries. I start my open labs tomorrow, so I really have to get done a lot of pre-labs too. So
Oh my gosh. Sorry.
no, you're fine. No, I don't mean that I don't mean that. So you're good. But
All right. Well, thank
okay.
you. I appreciate it so much.
You're welcome. No problem. Good luck on your exam tonight, and I will see you on Thursday. Oh no, vote. I gotta go on there. But I sent out an announcement because this next week I have my OChem lab, so I sent out an announcement about how you guys have to vote for your last few office hours on a time.
Oh, okay. Okay.
So just check out the
I will do
announcements.
that. Got it.
Okay.
Thank you.
You're
And
welcome.
have a good night.
Thanks, you too.
All right. Bye.
Bye.